Hello, welcome back to the maintenance course. Today we have a fresh new topic again, the physics-based models for predictive maintenance. And we will see how we can improve maintenance using physics in a predictive environment. And this is, in a nutshell, the idea for the lecture today. For table of contents, we have this one, which includes 4 major topics: the introduction, of course, Markov models, including Markov chains. We will also have a very brief slide on digital twins, what they are and what we can do with them. And we complete the lesson with filtering approaches with a glimpse of the Kalman filter. Today we will be studying physics of failure models. And what do I mean by this? There are 3 approaches in predictive maintenance. So whenever we want to predict failure, we can have 3 different approaches: the data-driven, the physics modeling, and the hybrid modeling. And as you can imagine, the hybrid modeling involves the physics modeling and the data-driven modeling in one go. Today we will focus on physics of failure models, which are models that are mostly based on physics, on first principles, on equations, on some kind of reasoning that involves physics. And it makes sense to develop physics of failure models because degradation is closely related to physical, chemical, mechanical, thermal, and also electrical and other mechanisms that evolve over time. And if we know the physics, we can provide extra information, we can provide better models that are more accurate, but this also has some limitations. Can you think of them? Well, first of all, it requires extensive expert knowledge, so you really need to know the physics of that specific system. And so it's a custom simulation that you need to develop each time you have a new system, which can be very time-consuming. And another limitation is that physics is an approximation of the real-world behavior. It's never a perfect replication. So we are always limited to a certain extent if we only rely on physics. And we will study 3 types of physics models: the Markov models, the digital twins, and the filtering approaches. The Markov models involve knowing the physics of the evolution of degradation, so that we know how many states we will go through in the lifetime of the equipment, and that's the knowledge that you input into the model, the physics knowledge. In the digital twin, the knowledge is all the set of equations and first principles and finite element simulations that you can include in the model. And the filtering approach, that includes the Kalman filter or the particle filter, are just state space models, which means they are recursive and they try to calculate the state of the system at each moment based on real-world information and on physics. And we will start by the topic of Markov models. Markov models are nothing more than stochastic processes, which are tuples or collections of random variables. In our case, we consider that each random variable is a state. So the state in our case, the system is at a given time. And all Markov models are governed by a crucial property that we call the Markov property. And it says that the future depends only on the current moment and not the past. So if you have an x of t plus 1, it only depends on the current state, so on x of t. It does not depend on x of 1, x of 2, x of t minus 1. It does not depend on those states. One model that I would like to talk about, that we're not going to study in depth, but it's a nice example of the Markov property, is the random walk or the drunk walk. We call it like that because it's about the story that comes with the model is about a drunk person. So imagine that you are drunk and you are not feeling so well, of course, so it's affecting you. And you do not have, and as you are walking, you do not know or you do not remember so well what you have done in the past. So you only know the current moment situation. And then you decide to go either left or either right, with equal probability of going left or right. So you do not have the notion of a path before you. You only know the current moment. And that's the entire idea of the Markov property. The future depends only on the current moment, on the present, not on the past. So I don't care in stochastic terms about the previous random variables. I care about my current random variable. And then I select where I'm going to go. In mathematical terms, we have this beautiful expression that tells us what I was trying to tell you, the Markov property. And essentially it says that the probability that the next state equals to a certain value, given the past history of random variables, is exactly equal to the probability of that same random variable t plus 1 being equal to that value, given that of what was observed in the current moment. Another property of the Markov models is the stationary assumption. And the stationary assumption tells us that the transition probabilities are independent of time. So whenever you are at x of t plus 1 equals to b, given that x of t equals to a, that's always going to be a fixed number, regardless of the time t. With all of these properties, we can say that if we work with Markov models, we are working with bounded memory transition models. Perhaps the two most famous models, Markov models, are the Markov chain and the hidden Markov model. In this lecture, we will talk mostly about the Markov chain, even though we have a small brief mention to the hidden Markov model. Importantly, we can classify or we can categorize or describe either the Markov chain or the hidden Markov model according to 4 dimensions. Some authors prefer to classify according to the state space, others according to the time dimension. It's more or less according to the preference of the author. But here we show the 4 categorizations. And as you can see, the Markov chain, which is the model that interests us, is in a countable state space. So it's a finite number of states involved. In terms of time dimension, it's about discrete time. And it's fully observable in terms of states. So we know all the states in advance, not as in the case of a hidden Markov model. And it's autonomous because once we set the probabilities, we can simulate the system autonomously. Remember the case of forecasting with the weather forecasts? In Markov chains, we also use a classical example related to the weather. And the idea is that what's going to happen tomorrow depends only and solely on what happened today in terms of rain. So the probability of not raining tomorrow depends on the probability of rain, yes or no, today. And how do we construct a Markov chain in this scenario? Well, you have to create 2 states, the state of raining and the state of no rain. And according to that, you fluctuate between raining and no rain according to the probabilities. And then you can also have as support the transition probability that we derive from the finite state machine. In maintenance, we use Markov chains to capture the evolution of the states of degradation of the system over time. So the Markov model, or in this case the Markov chain, can be used to model the different states of a system, such as, for instance, I can choose 4 states: healthy, start of degradation, degraded, and failed. Or I can choose just 2 states, degrading and then faulty after a failure occurred. When you have a Markov chain, you have 3 concepts that define the Markov chain: the finite state space, the state space, the probability transition matrix, or just transition matrix, and the initial state vector. So I will give an example of a system in maintenance that was in 2 states, degrading and faulty. In that case, the state space is the set with the states degrading and faulty. If this was a general system, you could consider n states, and the state space would be the set of all those states, from S1, S2, S3 to S of n. The probability transition matrix is another concept of the Markov chain, and it defines how you progress from one state to the other. So imagine that you have n states. You would have to make for each state the connection with the other state in terms of probabilities. So you can go from one state to any other state according to the transition probability matrix. In our example, we only have 2 states, so this gives 2 multiplied by 2 transitions. So we have, for example, the probability of going from the degrading state to the degrading state, and that will be, in our example, 0.8. If we go from the degrading to the faulty, that is 0.2. Notice that if you add these 2 probabilities, you get a probability of 1, because you always have either to be in the same state or to go to another state. So the set of probabilities have to add up to 1. But everything needs to start somewhere, right? And in this case, we need the initial state vector that tells us if we're going to start in the degrading or in the faulty state. Because I always start at the degrading state in my example, I need to set the probabilities to 1 and to 0, because they need to add up to 1. If the system was more general, then we would have a Markov chain with initial states probabilities equal to the number of states. So I would have a probability to be in state 1, a probability to be in state 2 at the beginning, and so on. There are many cases in which you know the states on which you are. If it's raining, if it's not raining, you know because you can observe the state. But there are scenarios where the states cannot be directly observed, such as, for instance, I never know the state of degradation of a system. I have some signals that point to the fact that it's more degraded or less degraded, but I will never know for certainty. I do not have a magic wand that allows me to go inside the system and get a magic number that tells me the degradation from 0 to 100 or from 0 to 4 states. I do not have that. But fortunately, someone invented the hidden Markov model. And hidden Markov models have essentially the same structure as a Markov chain, but they have what we call the observations. So for each state, we have what we can observe that comes out of that state. And that's the outcomes or the observations. And we can model different things because we know the probability of the emissions of a certain state to emit a certain observation. And we can more or less figure out, for example, the state that we are according to the observations that we make. I would like to leave a brief note on digital twins. And what are digital twins? It is something that a lot of authors are studying right now, because the idea is to create a high-fidelity digital model of an equipment, such for instance an engine, and according to how the engine is providing data, health monitoring data, you update your virtual system to make it equal, to make it twin to the physical system. For quite some time, I always thought that the Kalman filter or the particle filter were scary filtering approaches. But I think it's important to understand them because they're very, very useful, especially in maintenance and in lots of different fields. And they helped the progress of many aerospace applications. So it's kind of worthy to spend some time trying to understand them. That's my message. So let us start by giving an overview to filtering techniques. What is the idea behind filtering techniques? Well, filtering techniques have this amazing power that is to combine, to fuse information, even if some of this information is uncertain. And the beauty of it is that you can integrate expert knowledge based on equations to make all of this combination and estimation at the same time. And we have here this very, very, very complex diagram, not so much. But what is the idea? The idea is that you have a system and that you try to model the system with a filtering approach, like for example, a Kalman filter. And then you have two pieces of information. The physics that go inside the Kalman filter, and you're going to fuse your monitored signals with information from that physics. That will give you the healthy parameter that you would like to have if the system was in perfect conditions. But the reality is not like that. So we can match the observed measurements with the predicted measurements, the healthy ones, the perfect ones, and we get the residual. And if that residual is very large, we know that we face an anomaly and we are closer to failure because we are distancing ourselves from the expected behavior of a healthy system. And that's in a nutshell the idea of the filtering approaches in maintenance. And let me give you an example of how to use the Kalman filter or any other filtering technique to perform data fusion. So imagine that you had a car and you wanted to know the exact location of the car as it is moving. And you have in the car three sensors that are uncertain. They do not give you with absolute certainty the exact position of your car. So if their separates are uncertain, maybe together they can be more certain, more accurate. That's the idea of the data fusion in the filtering approaches. It is common to use a Kalman filter to perform this operation, and usually what the framework is this. We know the GPS, the IMU, and the odometer measures, and we know how to transform them into X and Y coordinates. Using the GPS, the IMU, and the odometer, we will make it go inside a Kalman filter, and we, based on these three pieces of information that basically tell you the same, we will provide an even better estimate of the position of the car. But sometimes we need to establish an unknown parameter based on related parameters. I'll give you an example. Imagine that you are on Earth and you want to go to Mars, and you want to go on a rocket. And you need to know, for example, the internal temperature of the combustion chamber. And you do not have access to this variable. It's too hot inside the rocket to know its exact internal temperature. But you know other things that are related, so how much fuel you're wasting at each moment, the external temperature, and you also know the physics that relate all of these variables. So you can use a filtering approach in this case. The idea behind the Kalman filter or any other filter approaches is always the same. We have a loop, and in that loop we have 4 steps. The first step being the prediction. So we predict what is going to happen to certain set of variables according to physics equations and to the information that comes before in the loop. Then we make our estimations and we measure what's happening in the real world, which always happens with some set of uncertainty. So we're trying to decrease the uncertainty of those measurements. So we pick up our perfect variables from physics, we compare them to the empirical ones, and by merging this information we correct our predictions. In the follow-up step, we update our predictions and we start the loop again. This is, in a nutshell, the idea behind filtering approaches. So this is the diagram that illustrates the schema of the Kalman filter. And here you see 4 boxes and a loop. The first box that I would like to pay attention to is the initialization box, where we define the initial state variables for the entire system one time in the beginning. That initialization goes inside the predict step that tries to predict the state and the uncertainty of the state to the next step. Once we have that information, we will merge it with real-world measurements. By merging the information that comes from the predict step and the measurement step, we will have information about the state at that moment, and we can do several things with that information. It's an output. But then we go again inside the loop to the predict state, and everything starts again. It is important to, before I explain the Kalman filter mechanics, to establish the variables that we are going to play with. And one of those variables is the state vector that holds the state variables. In the case of the rocket example, we can consider the state being the internal temperature or the external temperature, the pressure, the heat energy, or for example the capacity of the chamber. All of those variables are things that I want to know with exactness. I want my system to calculate them as the best they can. Some of them I will measure, some of them I will not. But when the update step ends, I want to have all of those variables. There will also be variables that have a very low of uncertainty, very low level of uncertainty, and those are the control vectors, in the control vectors. So, for example, the fuel. And there is always an uncertainty, a deviation from the reality regarding the state vector. For that reason, we create this variable that we call the process noise or the process uncertainty that has, for each variable, has the uncertainty of our state estimations. But I also talked about measurement, right? So we need 2 vectors, one to hold the measurements and one to hold the measurement uncertain. So how unsure I am of each variable at each time, and that's the measurement uncertainty. So how does the Kalman filter work? Let's start by the simplest and most basic step, the initialization. The initialization is performed only once, and it provides three parameters. The initial system state, so you will have information about the beginnings of the internal temperature. Of course, you don't know it, but you can provide an estimate, the external temperature, and so on. Also the initial control values, how much fuel you will have in the beginning. If you can't know it for certainty, try to make an estimate. And then you have the initial state uncertainty. How uncertain are you of setting those values? And even if you are not precise in your values, the Kalman filter can still converge close to the true measurements over time. After you initialize your variables, you can start predicting. In the predict step, we have two equations that are interesting. The state extrapolation equation and the uncertainty of the state extrapolation equation. The state extrapolation equation will predict the next step of all those variables, the internal temperature, the external temperature, and so on, by correlating them with each other and using physics. And this equation that I'm going to show you assumes that you have an F, that is the state transition matrix, that holds the information about how the variables in the state vector are interconnected in terms of the future. So how do I project the state vector one step ahead? And the G function, will help you to project the control variables. So you have these two matrices, the F and the G, that will help you project both the state and both the control. If you have a state extrapolation equation, you also have a covariance extrapolation equation or uncertainty of the state extrapolation equation. Long names, but it's just for you to know how we call them. In the extrapolation of the covariance, we extrapolate the uncertainty associated with our estimate of the next state. So if I'm making a prediction, I expect, or on average, I have more or less an idea of how unsure I am about my prediction. And that goes into the estimate of the uncertainty. Because the Kalman filter is grounded on the idea that there are measurements, real-world information, and physics knowledge that should be merged, there is the concept of the measurement step, where we received measurements from the real world inside the Kalman filter. And one such measurements could be, for example, the exterior temperature of the rocket for several times. So we need to have a measurement vector. Once we have these measurements, we can merge them with our state estimate variables. So it's in the state update step, and what we will be doing is we have a prior state estimate and the associated uncertainty. It's like a normal distribution, and we have the measurement estimate that has uncertainty to it, and it's also another normal distribution. And what we are going to do is calculate the posterior state estimate based on those pieces of information. And this is essentially, and in a nutshell, the core of the Kalman filter, to merge the measurements, the real world, with the physics and the things that come recursively from before the loop. The Kalman filter is an optimal filter, This means that it combines the measurement with the prior state estimate in such a way that it minimizes the possible uncertainty of the current state estimate. So we're going to try to squeeze a little bit the normal distribution of the state estimate according to the measurements, and this, in the Kalman filter, is done in an optimal way. But this can be controlled, and it can be controlled with a variable that we call the Kalman gain. And the Kalman gain is very important because it uses the uncertainty of the state and the uncertainty of the measurement to try to come up with who should I give more weight, to the state or to the measurement. And if the Kalman gain is close to 0, it means that the state uncertainty is very low. And perhaps the most important and the most beautiful equation that we have in the Kalman filter is this one. It estimates the next step of the state based on the previous step, using the Kalman gain to weight the measurements and the observations that we make in the real world. But, and not the least, don't forget about the uncertainty of the state. We also need to project it into the future, and for that we use this very long equation that will tell us the uncertainty of what we have just calculated. But you may ask, why do we need this in maintenance? How can we use this in maintenance? Essentially, there are two ideas, the Kalman filter and the measurements. The measurements will always follow their real-world trajectory, but the Kalman filter can be closer to a healthy system. Because if we say that the uncertainty of the state is low, it's going to follow the equations more than the measurements. It's still going to follow the measurements, but it's going to be closer to the perfect behavior of a healthy system, if we want. And if we calculate the deviation, the difference between the measurements and the Kalman filter state, we can know that we are deviating more and more and more, and that we are closer and closer to failure. As a last example, consider this real-world case study of doing maintenance with the Kalman filter. So we have this quadruple tank with 4 tanks, and they are all coupled. And you can see, or you are interested in the water level of tank 1 and tank 3. You know the equations that define the water level at tank 1 and at tank 3. And you know that those depend on variables that you can measure. The state space representation of your tank system is this one. So you have the state vector with the water levels, age of 1 and age of 3, and you obtain that based on input control variables and state control variables. So you're going to calculate the next water level based on the previous water levels and on some control variables. And you have here a progression of the Kalman filter versus the real measurements in terms of the water level at the first tank. And you can see that the Kalman filter in orange follows the physics behavior, so the perfect behavior, because I set the uncertainty of the Kalman filter to a very low value in terms of state. And then you have the measurements, and at some point they have an anomaly behavior. By comparing my Kalman filter with the measurements, I can detect this anomalous behavior. And I can say there was something weird about the water level at the tank. We should check them, for example. And that's a possible example of the Kalman filter. The Kalman filter is very useful. It was used with much success in many aerospace applications, but it has a problem. And the major problem, is that it assumes that the system that you are modeling is linear. And that is almost often not the case. It also assumes that the variables are normally distributed, such as the measurements and the state. And this is not always the case again. An alternative is the particle filter that thinks differently and doesn't make these assumptions, especially the linear assumption. And for that reason it is much more popular in maintenance than the Kalman filter. But due to its higher complexity, we are not going to cover it in detail in this lecture. I hope you have enjoyed the lecture, that you have learned a lot, even though it was a challenging lecture. I hope you have had fun with it. And thank you for watching, and see you next video.